Many of the properties and reactivities of atoms are controlled by the valence electrons of those atoms and how attracted those valence electrons are to the positively charged nucleus. So remember that electrons are negative and protons are positive, so there's an electrostatic attraction. The structure of the atom has the protons in the center and then layers or shells of orbitals holding electrons arranged around that center. The valence electrons are in the outermost layers of the orbitals. And the attractance for the valence electrons isn't as easy as simply taking the nuclear charge and multiplying it by the valence electron charge and then dividing by the distance between them. The problem is the electrons in the inner core are essentially blocking some of the nuclear charge from reaching the valence electrons. We say that the core electrons are screening the valence electrons. The reason this happens is because electrons repel one another, and even though the valence electrons are attracted to the nucleus, they're also repelled away from the nucleus by the core electrons that are in between them. So we'll consider a couple of examples, and we'll start with hydrogen, which only has one proton and one electron. So in the case of hydrogen, you have an electron that exists in a spherical s orbital around the proton, and there's nothing in between. So in hydrogen, the valence electron, the only electron, feels the entire nuclear charge, and we give that charge the symbol Z. A similar situation exists for helium with its 2 protons and 2 electrons. In this situation, helium's electrons, its valence electrons, are both in that single s orbital, and they don't have any charged particles in between them and the nucleus, so they also feel the full nuclear charge. Things get a little bit more interesting when we move to lithium with its 3 electrons. The trick with lithium is that there are now multiple shells. Lithium has the electron configuration 1s2, 2s1. This means that there's 1 electron in lithium's valence shell, and there are 2 inner electrons that are going to screen the valence electron from experiencing the full nuclear charge. Actually measuring how much nuclear charge is felt by the valence electrons is really tricky to do, and there are a number of different methods. We're going to use a very simplistic version that explains enough of the detail that we'll need. The model that we'll use is the effective nuclear charge, Z effective, is equal to the nuclear charge, Z, which is just the number of protons, minus the screening electrons, S. So the number of protons in lithium is 3, and the number of screening electrons, the number of inner core electrons, is 2. So that means lithium's effective nuclear charge, the charge felt by the valence electron in lithium, is just 1. And we don't have to draw these diagrams to work at effective nuclear charge. We can use the information from the periodic table and electron configurations. One easy way to do it is write the number of protons in an atom and then draw the electron configuration next to it. And we can do something similar with beryllium. Beryllium has 4 protons and it has 2 screening electrons, 2 inner core electrons, and that means that its valence electrons experience a 4 minus 2 Z effective. And if we move to boron with its 5 electrons, we see a similar thing happen. Boron has 5 protons and it has 2 screening electrons. So you might have noticed that the effective nuclear charge, the Z effective, increases as you move from left to right across a row in the periodic table. So you keep adding protons, and the number of core electrons stays the same. So when you move left to right across a row, valence electrons are going to be more strongly attracted to the nucleus, and therefore harder to remove. The effective nuclear charge is also going to increase as you go down a group, but it won't increase very much. So the left to right trend in effective nuclear charge is pretty easy to understand. Within any given row, you have a consistent set number of core electrons. The only things that are changing are the number of protons and the number of valence electrons. And the valence electrons don't contribute to the effective nuclear charge. So the only thing that really matters is, as you go left to right, the number of protons increases, but the number of screening stays the same. The effective nuclear charge also changes as you go down a group. It doesn't change very much, but as you go down a group, the Z effective increases very slightly. We're going to look at this by examining lithium and sodium. If you calculate the Z effectives for lithium and potassium, two elements that are in the same group, you'll find that if you use this simplistic model, they're exactly the same. But in reality, sodium's Z effective is actually a little bit larger than that of lithium. So consider that the screening electrons within sodium are in different shells. 2 of them are in the n equals 1 shell, and 8 of them are in the n equals 2 shell. It's important to remember that the n equals 2 shell is going to be so much larger in volume than the n equals 1 shell. And this means that the 8 electrons that are in that n equals 2 shell are spread out in space quite a bit. And because they're spread out so far, they effectively act like a much more diffuse screen. And they don't repel the valence electrons as much. So if you use a lampshade analogy, where the number of protons represents how bright a light bulb you have, and the number of core electrons represent how thick your lampshade is, a bigger shell represents a lampshade being stretched to be a much larger shape, but having the same amount of material, so the lampshade effectively gets thinner. If you look at the horrible drawing I've made of light bulbs covered by lampshades, you can see in the diagram on the left, if you put 8 electrons into a full S&P shell, like in an n equals 2 shell, you have a certain amount of electron density. If you look at the example on the right, you can see that the lampshade representing the n equals 3 S&P shell is much larger. It still has 8 electrons in it doing the screening, but those 8 electrons are stretched far thinner. They're much less effective at screening the charge. And because that screening is less effective, the valence electrons are going to experience a slightly bigger effective nuclear charge. And this effect is not particularly large. The valence electrons in sodium do not feel an enormously larger effective nuclear charge than those in lithium, but it is slightly larger. And the same thing would be true for potassium, which would have a slightly larger effective nuclear charge than the sodium.